So we're now going to discuss a way of choosing a discriminant function. And this is going to lead to what is referred to as the maximum likelihood discriminant rule. I'll have to abbreviate that to the ML discriminant rule. So remember the situation. We're assuming we've got G populations, pi 1 up to pi G. But now we're going to assume that the cases in each population have a known distribution. So we're going to assume that the cases in population 1 have a distribution that has probability density function f1 of x, and so on. Okay, so the cases in population G have a density function pi g of x. Okay, so in other words, we're going to assume that x has a density fj of x. So the ML decision rule, or the ML discriminant rule, the maximum likelihood discriminant rule, says classify observation x to population j if fj of x, if the likelihood of observing x if it's in population j is bigger than fi of x for I not equal to j. Or another way of writing that is to say our decision rule d of x, so remember d is a map from Rp to the population label, so from 1 to g in this case. So d of x is the value of the argument j that maximizes fj of x. So what do? We take all these densities, and when we have a new observation x, we just evaluate each of these densities, and then whichever has the highest likelihood, we say x is from that population. Okay, so let's have an example. Let's suppose that we've got population 1, let's suppose that has a normal mu1 sigma 1 squared distribution, and population 2, let's suppose that has a normal mu2 sigma 2 squared distribution. So univariate observations. Okay, so x is just in R here. So what does that look like? Well, if we've got mu1 here, say, and mu2 here, we've got one density centered around mu2, okay, and another density mu1, I suppose, that has higher variance. It's a rubbish drawing, but that's the situation we're imagining. We've got two densities. So this is the density f2 of x, this is the density f1 of x. The ML discriminant rule classifies x to pi 1 to population 1 if f1 of x is bigger than f2 of x. Well, where is that the case? Well, we can see there's a switchover point here. So any value of x in this range is going to be, anything there is going to be classify as population 1, whereas anything in this region we're going to classify as population 2. Now we can do this numerically, of course, but in this case it's simple enough to do it mathematically, so let's work out what this cutoff point is here. Where does one density become bigger than the other density? So let's see if we can work this out. So when is f1 of x bigger than f2 of x? Well, that's if and only if f1 of x over f2 of x is bigger than 1. The densities are positive, we know that. So if we write these densities in, we can see that we're going to get, this is going to be sigma 2 over sigma 1 e to the minus a half sigma 1 squared x minus mu 1 squared plus a half over sigma 2 squared x minus mu 2 squared bigger than 1. Well, let's take the log of both sides now. So we take the log, we get if and only if the log of sigma 2 over sigma 1 minus the term in the exponent is bigger than log of 1, sorry, which should be 0 here. And now if I collect terms in x, what we get is this is if and only if. Well, let's collect the x squared terms up. We're going to get 1 over sigma 2 squared. Okay, so we get an expression like this. So this, you'll note, is a quadratic in x. Okay, so we've got an x squared term, an x term, and a constant here. So this is of the form ax squared plus bx plus c. Okay, and if we want to find where it switches from being positive to negative, we can just solve this for equal to 0, okay, and we can solve this. So let's pick some values for mu and sigma. So let's begin by letting sigma 1 and mu 1 be equal to 1, and mu 2 and sigma 2 equals to 2. In this case, the quadratic we computed reduces to an expression like this, so minus 3/4 x squared plus x plus 2 log 2, and we want to find where that is bigger than 0. Well, if we solve where it equals 0 using the quadratic equation, the quadratic formula, we find that it equals 0 at x equals minus 0.5 and x equals 2.18, and thus if we plot this, we've got our two densities here, so we've got population 1 with mean 1, variance 1, population 2 with mean 2, variance 2. Okay, and we can see where they cross. They cross at minus 0.85 and 2.18. And so if we apply our ML discriminant rule, we're going to classify the population 1 if x is in this region, or we're going to classify to population 2 if it is in this region or this region. Okay, so notice in this case we don't have a connected decision region. We don't have a connected discriminant region. And we said in the previous video they should be connected. Well, that was for linear decision rules. Here we've got a quadratic decision rule, which is why we've not got connected regions. If we pick different values for sigma 1 and sigma 2, okay, so in particular, if I let sigma 2 be the same in both cases, so if I let sigma 1 equal to sigma 2 and we're both equal to 1, say, then we get cancellation of this squared term here. If sigma 1 equals sigma 2, this term cancels, and we're just left with a term that is linear in x. Yeah, we don't have the square term, we have an x term and a constant term. So particularly for the numbers I've chosen, we get a classifier like this, a discriminant rule like this, okay, which is minus 2x plus 3 bigger than 0. So in this case, it's easier to solve. We're just going to find that we classify to population 1 if x is less than 3 over 2, or population 2 otherwise. Okay, that makes sense, right? We pick the halfway mark. We've got two populations, one would mean 1, one would mean 2, the same variance. They cross over midway between at 1.5, and so we just classify to population 2 if we're over here, population 1 here. So in the case where we had a common variance, we have got a connected decision region, and we get a linear decision rule. So now we'll consider the situation where each of the populations has cases that have a multivariate normal distribution. So we'll assume that for population J, that the x's we observe from population J have a multivariate normal distribution with p dimensions, where we've got the population mean, mu j, and sometimes we'll call this population centroid, okay, the centre of the population, if you like, and a covariance matrix sigma. And just note here that we've got the same covariance matrix for all the populations. We can let the covariance matrix differ between populations, but as we'll see, that leads to a quadratic discrimination rule. That leads to a quadratic discriminant rule, whereas if we have a shared covariance matrix, then we get a linear discriminant rule. So if we think about the density of each population here, the density of our multivariate Gaussians is the determinant of 2 pi sigma, negative square root, and then we've got e, so minus a half, and we're going to have x minus mu j sigma inverse x minus mu j. And so our discriminant rule, we said, is the value of j that maximizes this. And I think it's easy to see that to maximize this, you need to minimize the exponent here, because it's got a shared covariance matrix. There's no j appearing in the constant here, so we can ignore that. So this, maximizing this with respect to j, it's the same as minimizing with respect to j, x minus mu j sigma inverse x minus mu j. We go further than this. If we expand out the brackets here, or I missed some transposers, if we expand out the brackets, we're going to get this is x transpose sigma inverse x minus 2 lots of mu j transpose sigma inverse x plus mu j transpose sigma inverse mu j. Now this term here doesn't depend upon j, so we can ignore that in the minimization. So all we need to think about is this term here. What minimizes this? Well, this is the same. I'm just going to take a minus sign out here. This is the same as maximizing, with respect to j, delta j of x, where delta j of x is going to be our discriminant function, and it's equal to this bit over here. So it's going to be 2 mu j transposed sigma inverse x, minus mu j transposed sigma inverse mu j. So this is the form we had before. This here is our linear discriminant function. So the way we do discriminant analysis with a bunch of multivariate normal populations is we evaluate the discriminant function for j equals 1 to g, and then we classify x to the value of j that maximizes this. Okay, so we'll see an example of this in a moment. So let's just say in practice we won't know mu j or sigma, and so we have to estimate them from data. So if we're given data x1 j up to x, let's say nj j from population j, then we use the estimate of mu j to just be the sample mean of them. So let's say mu j hat to be 1 over nj, the sum of the x I j, I equals 1 up to nj. So the sample mean of all those observations we have from population j. Then we also want to estimate this shared covariance matrix sigma. Well, how do we do that? We have to be a little bit careful here. We let Sj be the covariance matrix for population j. So this is the estimated covariance matrix of x1j up to x and j of j. Then our estimate of sigma is to pool all these estimates. So there's various forms of this we can use, but essentially something like 1 over n or 1 over n minus g, for g groups. So the sum of j equals 1 up to g of nj sj. Okay, so that gives us an estimate of the covariance matrix sigma for all the populations. I just want to note here that this is not the total covariance matrix. Yeah, I've used different population sample means for each of the populations, and so this is not the covariance matrix of all the data.